decentralized real-time collaborative text editor using WebRTC and CRDTs. If you don't know what those words mean or acronyms mean, don't worry, I'll get into them in a bit. Before we begin, I just want to give a quick demo of Conclave. Okay, great. So this is Conclave right here. It's, I guess, a little hard to see, but it's basically a text editor. I can write stuff in it, like Hello World. It supports Markdown. And then so if I wanted to invite someone to collaborate with me, I would typically copy this link, send it to them through Slack or through an email. But in this case, I'm just going to open up a new tab real quick. And so you can see when that tab opened, the new peer on the right side was linked to me. And so if I go to their tab, they sync up to me. And so I can also write something here. And if I go back to my original tab, there you can see that there's a remote cursor. And then so I can see who's typing and where they're typing at. And then the one thing that we were able to add that you might not see in other text editors is actually video support. So if I were to click on their name, I want to chat to Grasshopper, you can see that they're now getting an incoming call from Jackal. If I answer this, then a little moto pops up, and then I can talk to them, wave, and then minimize it, and then end the call as well. So that is Conclave in a nutshell. So I just want to give a quick shout out to the team. There's Elise Oliveras in San Francisco, California, Nitin Savants in Minneapolis, Minnesota, and then myself in Brooklyn, New York. As you might notice, we are a remote team, and that's kind of why we decided to build a collaborative editor in the first place, because as a remote team, we're using Google Docs a lot to collaborate. And so when it came time for us to actually build a project together, the first thought was Google Docs. How does it work? What's behind the scenes? And so the best way to learn was to build it ourselves. And so that's kind of how Conclave was born. And so to give an overview of what I'll be talking about tonight, the first is going to be text editor basics, just how does a basic text editor work, so we can kind of get in the same field and I can advance your knowledge from there. Next, we'll be talking about primary challenges that a team like you or yourself or that we faced building a collaborative text editor, and also the solutions we came up with. Third is going to be the evolution of our system architecture. That's going to involve talking about the limitations of a central server and then why we decided to go with a more decentralized architecture. And lastly, we're going to talk about optimizations that our team made for Conclave, and then also future plans that we have for Conclave and how you can get involved as well. So the first things first is going to be, what is a text editor? So for our project, we defined it as a list of characters in a document stored in order based on the user's intention. So the user kind of defines where each character goes. Each character is going to have two basic properties. You have a value, which is the value of the character in the text editor, so the letter value. And then also an absolute index. So kind of like elements in an array, each element has their own index. Character's going to have an index as well. And there's two basic properties to kind of concern about. It's going to be insert and delete operations. And so while you're typing onto an text editor, each stroke is interpreted as insert or a delete if you use a backspace. But it's going to be interpreted as an operation at the index where the cursor was. So if I do an insert at the beginning of the line, it's going to be an insert of C at index 0. Same with delete. And you also notice on the right side that the indexes of each character shifts back and forth depending on the operation. And so this works well for a local text editor, but we're trying to build a collaborative text editor. So what does that mean exactly? So we defined it as users in different locations collaborating on the same document at the same time, often on the same word, even the same line. And so each user is going to have their own copy of the editor or their own copy of the document in their machine, so they're all looking at the same document. And then whenever a user makes a change, that change is applied first locally and then broadcasted out to everybody else so that they can incorporate that change and become eventually consistent. And so as you might imagine, there are quite a few challenges with this. The first challenge being, how do we merge conflicting and concurrent operations in a consistent manner so everyone kind of stays the same? Also, how do we reduce the latency to the point where everyone feels as if they're collaborating in real time? And third, there's extra concerns when it comes to scaling a real-time application, especially if you want to house many concurrent users at the same time. And so for our team, in order to tackle all these different challenges, we wanted to start with the most basic system architecture and then kind of scale from there. So the most basic system we can think of was just two users and a central relay server. So each user is making edits, and it's getting passed through the relay server. And then, so they can just make edits from there. And so my team was wondering, can two users stay consistent in this manner? Can they collaborate, stay consistent? Or are there extra edge cases that might pop up just in this scenario? And it turns out there are. Let's say there's two users, and they make concurrent inserts and deletes at the same time. So user 1, user 2 both start with hats. and say user 1 inserts a C at the beginning of the line, while user 2 deletes the first character. So when those operations are sent across the server to the other user, user 1 is told to remove the first character, so they get hats, while user 2 is told to insert a C at the beginning of the line to get cats. Well, hats and cats are not the same, so something went wrong. And the reason for the inconsistency is because even though we're using the same operations, they're being applied in different orders. So user 1 had to insert first and then delete, while user 2 did a delete and then an insert. So that's the reason for the inconsistency. And another problem happens when users make concurrent deletes. So if both users were to delete the same character at the same time, so in this case they both delete H, they get ats, but then those operations are sent across again and reapplied a second time, so they end up with T. So even though they stay consistent, it's not what either user wanted. We lose user intention. Each user wanted to have ats, and so they lost that. So based on these edge cases, we kind of came up with two properties that we wanted to maintain in order to have consistency in our system. The first property is called commutativity. What that means basically is just depending, no matter the order of operations, if they're the same operations, we want them to converge in the same state. So insert plus delete should equal a delete plus an insert. And same with, so the next property is called idempotency, and basically what that is just given a single operation, no matter how many times you apply that operation, it should have the same result. So in mathematics, you can think of multiplying a number by 1. No matter how many times you multiply a number by 1, it's the same number. And so the reason why we're not maintaining these properties is because we're using these absolute indexes. So I showed before the absolute indices change depending on the operation, and so we can't depend on them to stay consistent. So how do we go about fixing this? What can we do to solve these issues? So my team did a lot of research and reading a lot of white papers, and we found two possible solutions. The first one is called operational transformation. I'm going to refer to it as OT. You might be familiar with operational transformation if you've worked in distributed systems or if you've built or worked on collaborative tools. And it's essentially just a really complicated algorithm. And what it does is that it looks at concurrent edits when they happen, and it detects how each edit is going to affect the other. And so it can transform each edit to basically stay consistent. And this is pretty complex to do. So the best way for OT to guarantee consistency is to be implemented on a central server. And so we're going to need to have a single source of truth. So to show how that might work in a real scenario, if you go back to our last example with hats and cats, once the insert and delete operations, the concurrent ones, go to the central server, the OT algorithm is going to detect that that insert operation of C at index 1 is going to shift the index of H. So we need to transform the delete operation from index 1 or index 0 to index 1. And so now when user 1 gets that delete operation, they're going to stay consistent. And there's not going to be any errors. And the same thing, our OT can also work with idempotency. So when each user deletes the same character at the exact same time, it gets sent to the OT algorithm at the server. And then the server can detect that these are the same operations. So they shouldn't be applied again. So they're just not going to send them to the other users. So you can keep idempotency in this manner. And so OT is a very viable solution. Many products have used OT. Google Wave was one of the first collaborative tools to really popularize operational transformation. Google Docs still uses it to this day. And in terms of the open source field, you have Etherpad, which is also a collaborative editor that uses operational transformation. The problem, though, is that the conclusion that my team got from these products is that OT is very tough to implement. This is a rather famous quote from Joseph Gentle, one of the engineers of Google Wave. And it basically says that OT sucks to implement. There's tons of trade-offs, tons of different algorithms all stuck behind these white papers that you have to read. And then Google Wave itself took 2 years to implement. So as a remote team trying to build a cool open source project really quickly, you only have 2 years to do it. So we decided to skip on OT. So the other solution that gave us was called conflict-free replicated data types, also known as CRDTs. And these were created by researchers who are trying to simplify OT, because OT is really complicated. And basically what it is, it's just a really complicated data structure, and it uses a lot of metadata. So it moves the problem-solving logic from the algorithm to the data structure. So it allows for much simpler algorithms, and it allows for a kind of overall simpler. So while it uses more metadata and it is a more memory-intensive solution, the overall solution is much simpler. So it's much faster to implement. And another nice thing about CRDTs is that it's a distributed data structure. So each user has their own copy of the CRDT on their machine, and so that means we don't have to have that central server bottleneck like we do in OT. And the way that CRDTs guarantee commutativity and idempotency is by basically treating each character like a unique object by actually turning each character into a unique object. So what I mean by that is, say I were to insert this A into my editor, the CRDT would take that A and transform it into an actual character object with 3 properties. It's going to have a site ID, which is just the ID of the user who created it, so every user has their own ID. It's going to have a value, which is just the letter value, and it's going to have a position. And so this position is different than the absolute index that we were using before. So this position is relative and unchanging. So what I mean by that is every character that is inserted into the editor is given a position that is greater than the character that's before it, but less than the character after it. So in this case, if I were to insert this A at index 1, my CRDT would look at the H object, or the H letter at the very beginning. It has a position of 8. It looks at the T, which has a position of 9, and generates a position that comes in between it, in this case 8, 5. So you might be wondering, why is 8, 5 less than 9? What's the criteria that I'm using to compare positions together? And so another way of looking at this, or looking at the characters, you can think of the characters in the document like nodes on a tree. And so back to our HT example, if I wanted to insert an A in between them, well, there's no whole number integer that comes between 8 and 9. So in order to generate a value in between them, I'm going to have to branch off of H and go to the next level of the tree and generate a number on the next level. So whenever you traverse the tree now in order, you get HAT, so you get hat. So what I've essentially done here is create a fractional index. So A is going to have a value of 8.5, and how we represent that in code is just an array of values, so 8 and 5. So that's where that is coming from. So to show how a CRDT works in kind of a real example, you can go, so that whole process is kind of represented here. So you can see the first box right there is showing that you're retrieving the position of the character before it and the position of the character after it. And the second box is checking the difference between them. So the difference is exactly 1. Then we're going to do a recursive call, branching off of the character before it and then generating a new ID. So this is basically just how we generate positions in between characters. And so to show how CRDTs work in a live example, you can go back to our previous example. In this case, I've included the relative indexes as reference. And so now let's say that users both start with cats. User 1 inserts an H at index 1, but that index is turned into a relative position of 1.5. User 2 deletes the character C with a position of 1. So now when those operations are sent across, user 1 is told to delete the character C with position 1, and then user 2 is told to insert an H with a relative position of 1.5. So it can find the correct position and insert it there. And so this also works with deletes. So if we have concurrent deletes, each user deletes the same character. Then when it's sent across, so in this example, user 1's going to look for that character H of position 1 in their CRDT. They're not going to find it, so they already know they deleted it. So they can just ignore it. So now we've maintained commutativity and idempotency. And so with the CRDT in place, we've kind of solved our merging conflicts problem, but we still have the problem of latency and scaling the network. So in order for our team to really tackle these issues, we had to look at our current architecture and see if there's any flaws or any limitations that we can improve upon. And so at the time, this was our architecture. We had multiple users, each with their own copy of the CRDT. We had a central relay server where they're all sending the operations through. But there are some limitations with this, one of them being a high potential latency between users. And what I mean by this is, say we have 2 users located in California, and let's say they're neighbors, so they're really close together, but they're connected via a server in New York. So in order to communicate with each other, each operations needs to be sent through that server in New York and back. So you got a round trip of potentially 200 to 300 milliseconds, and that affects the real-time feel of our application. If they could talk directly to each other, it would only take about 10 milliseconds. Another issue is that it takes money to scale a central server, and the more users you have, the more WebSocket connections you have, the more work the server needs to do. And so in order to scale that, it's going to take money and resources. Whether you vertically scale it or horizontally scale it, it's going to take money. And so as a team trying to make a little open source project, didn't have a lot of resources for that, so we didn't want to spend too much money on this. And then the third is it introduces a single point of failure. So if our server ever goes down, then we can't collaborate and the app's dead, pretty much. So we realized we could tackle all these issues if we switch to more of a peer-to-peer architecture, where each peer acts as both a server or a client and a server. So whenever one peer makes an edit, it will get sent to the peer they're connected to, and that peer is going to then pass on to the next peer, and then so every operation will get disseminated across the entire network. And so in distributed systems is known as the gossip protocol. So every user is going to gossip the next one until everyone receives the information. And then in terms of scaling, it's much cheaper to just add an extra node to our peer-to-peer architecture than adding a website connection to a central point. So that kind of solves our scaling as well. But it's nice to talk about peer-to-peer in theory, but how do you actually go about implementing a peer-to-peer structure, especially on the browser? So for Conclave, we use WebRTC, which is known as Web Real-Time Communications. And it's a protocol that allows users to connect directly to each other via a UDP connection. And so UDP is nice for us because it's also very low latency. And WebRTC allows users to establish a data channel. So users can send data directly to each other. In Conclave, we send JSON objects between each user. And then in order for users to connect via WebRTC, they need to know the location, so basically the public IP address of the other user they're connected to. So they need to communicate with a stun server. So to get a more high-level view of how WebRTC works, this is essentially a high-level view. One thing to note is that a server is still needed for WebRTC, but a server is only used to broker connections between users. No document information is ever sent through that signaling server. And so basically, if two users want to connect via WebRTC, they're going to communicate with the stun server near them to get their own public IP address. They're going to send it through the signaling server to the other user, and then once each user knows basically the location of the other user, they can establish a WebRTC connection and start communicating. And in the case where WebRTC doesn't, basically the connection fails, we have a backup turn server to send information to each other. And so WebRTC is nice, but there is one big drawback, is that while UDP is fast and low latency, it doesn't guarantee in-order packet delivery. So that's a big problem for us, because for a collaborative editor, we kind of depend on operations being sent in order. The reason for that is I can show you an example. Let's say we have 3 users collaborating together. User 1, user 2, so peer 1 and peer 2 are located very closely to each other, distance-wise, and then peer 3, let's say, is halfway across the world. So if peer 1 were to insert a character, peer 2 would pretty much immediately receive it because they're so close. And let's say that peer 2 wants to delete that character, that they don't like it. And so basically now what you have is 2 operations on their way to peer 3. And based on UDP and then the unpredictability of the internet, let's say that the delete operation gets there first. Well, what do we do now? Because if user 3 tries to implement that delete operation, they're going to look in their CRT, see that they haven't received that insert operation yet, or that the insert operation is not there, and they're going to think, oh, I've already deleted this. So they're going to drop that operation, which is bad because once they get the insert operation, they're going to implement the insert. They're going to have lost that deletion already, and so now they're inconsistent with peer 1 and peer 2. So now we're back to inconsistency. So in order to tackle this problem, we need to basically implement what is called a version vector and combine it with a deletion buffer. And it sounds fancy. Basically what it is each user has a hash table. The values are going to be the IDs of the users they're collaborating with, and the values are going to be the most recent operation they've seen. So every operation has a version, basically, a number, the counter of which operation that was. And so you can see in this little code snippet, whenever we send operations through to each other now, there's 3 properties. We have a type, so it's either a delete or an insert. There's a character, either the character we're inserting or the character we're deleting, and then a version. And the version is going to have the site ID and the counter of the user that generated that operation. So to show how it works, if you go back to this example, so now each operation has their version, so it has a site ID and a counter. And so once that delete operation gets to peer 3, they can check in their version vector. So in this delete operation has a site ID of 2, counter of 6. They can check their version vector, see that they've only received 5 operations from peer 2 so far, so they know that this delete operation is a new one, so they should incorporate it. However, since delete operations depend on the insert operations, you can't insert something that doesn't exist, we're going to put the delete operation first in a deletion buffer. Then we're going to process that buffer, And then once we process the buffer, we're going to check if there's any deletes there. In this case, there is a delete. And we're going to check the version of the character it's trying to delete. So in this case, it's trying to delete the character with set 81 and counter 24. It's going to check the version vector, see that they've only seen 23 operations from peer 1 so far, so they know that they haven't seen this operation yet. So they're not going to do anything with it. So once that insert operation comes in, they're going to incorporate the insert operation, reprocess their buffer to see if there's any deletes they can make. In this case, there is. So they're going to incorporate that delete operation, and you can see in the top right, now they've updated their version vector. So with every operation, they update their version. So that is basically how our version vector works. And all of that process you can see in this snippet of code. So this code runs whenever we receive a remote operation from a user. So in line 2, you can see that if it's an insert operation, we just apply it immediately because inserts don't depend on other inserts or any deletes. However, if it's a delete operation, we first push it to our buffer, and then after either a insert or delete, we process the buffer, and then we send it off in the gossip protocol. And then also, a nice thing about version vectors is they act as a fast guard clause to prevent duplicate operations. So you can see in the first line of code, if an operation comes in and we've already seen it, which is possible in a peer-to-peer architecture, we're just going to ignore it and just return early. So basically, with our version vector in place, we have a working application. So we have our CRDT that communicates with our version vector. We have a messenger class, which is essentially just a wrapper around a WebRTC connection. And so the messenger is responsible for receiving and sending out WebRTC objects. And then we have the local editor, which is just, in our case, we used a open source library called CodeMirror. I'm not sure if you're familiar with it, but we use CodeMirror for our editor. And then we have a controller that just basically communicates between all the working parts. And so at this point, like I said, we have a working application. But as we use the editor, we still realize that there's things we can improve upon. So I'm going to talk about some of those improvements right now. And so the first was to our CRDT structure and how it performed. And so we started off our CRDT with a linear array. That was the initial data structure for our CRDT, which is fine for small documents, but it can become really inefficient as the document grows and gets really big. And another issue we're running into is that there's a slow communication between our CRDT and our editor. So in this case, with CodeMirror, whenever you insert or delete a character in CodeMirror, it returns this position object that tells you the line index, or which line it's on, and then which index on that line. But since we're using a linear array, we have to linearize the object, that object. So we have to linearize your index, which involves retrieving the document, splitting it by new line character, and iterating across it to find the index. So that's a lot of overhead just for every operation that happens. So to basically address that, we just turned our CRDT into a two-dimensional array because that's how our editor was structured. And so now what we can do is we can take that position object that CodeMirror gives us and just pass it directly to our CRDT. So it's a very fast communication. And it turns out there's other improvements as well. So here's a small table showing the big O improvements of a linear array and a two-dimensional array. So for a linear array, search is log n, just because we can use a binary search to find characters. But with and log n is being the number of characters in the document. But with a two-dimensional array, you can use two binary searches, one to find the line, and another to find the character on that line. And so it improves to log L plus log C, L being the total number of lines, and then C being the total number of characters on that line. And assuming that L plus C is less than N, then it's an improvement. For inserts and deletes, with a linear array, it's O of N, just in the worst case if you're making changes at the beginning of the array. In a two-dimensional array, you're only ever operating on one line at a time. So the worst case is going to be O of C, C being the number of characters on that line. And then the find index is just referring to that linearization I mentioned before. So in a linear array, we define the index. So it was an O of N operation having to split the document. But with a two-dimensional array, it's now an O of 1 operation just because we can just pass along that object, and so we know exactly where it's occurring at. And so in Conclave, we actually created a performance script as well. And so we recorded how long it took each data structure to complete this performance script. The blue line is our linear array. You can see that around 100,000 operations, it takes around 14 seconds to complete, which is a little slow. But with a two-dimensional array, the orange line, you can see that it took less than a second. So that was a big improvement, and we were very happy with that. And then the next optimization that we made to Conclave was with how we dealt with the WebRTC connections and how we managed them. Because with WebRTC, it allows users can communicate directly to each other, but it's up to the developer to manage those connections between users. So one problem that we were running into was stranded users. So let's say we have 3 users collaborating together. Peer 2 and peer 3 are connected via peer 1, but what if peer 1 leaves? Well, now peer 2 and peer 3 are stranded. They can't collaborate. They don't know the other one exists, and so now we're kind of stuck. And so what we need is a way for peers to rediscover each other and keep collaborating. So we created what is called a network array, or some network list. And so what it is each peer maintains a list of all the other peers they're collaborating with. So even if they're not directly connected to them, they know that they're there. And so this list is updated whenever peers join or leave the network. And so if a person they're connected to leaves and they're stranded, they can just pick someone from random on that list, and then send a connection request, and then they can keep collaborating together. So it's kind of a dynamic architecture. So basically, at this example, if peer 1 leaves, they can remove peer 1 from the network, and then pick someone new. In this case, there's only one choice, so then they pick each other and then kind of keep collaborating. But can we proactively avoid those single points of failure? Because that was kind of the whole point of getting rid of our central server, was to avoid single points of failure. And so we created a load balancing algorithm. And we basically, it works via connection forwarding. So say that we have 4 users, all of them connected to peer 1. If another user wants to join, they're going to send a connection request to peer 1. And so what we did was we created a max number of connections that a user can have in this network. And so in this example, say the max connections is 3. So once peer 1 receives that connection request to peer 5, they can check the amount of connections. They have 3 already, and so they've reached their max. So what they're going to do is they're going to forward that request to someone else in the network. And so in this case, they forward the request to peer 4. Peer 4 can then check, okay, do I have too many connections? I don't in this case, because there's only one connection. So they will connect back to peer 4, and now we've effectively load balanced the architecture. But as you can see, this isn't the most, or there are still improvements to be made, because peer 1 still has somewhat of a single point of failure there. So that kind of leads me to my next slide, which is future plans. The first one is to improve the connection distribution even more. One idea that we're playing around with is secondary requests. I've kind of started implementing this already. But basically what that means is whenever someone joins the network, they're going to join whoever initially sent them that link first, but then they're going to send a secondary request to somebody in the network. So that way they always have at least one connection to fall back on. So if someone they're connected to leaves, they always are still connected to the network. Another optimization is going to be for mass insertions and deletions, because right now our CRT only works on a single character basis. So large mass pastes and cuts can be a little slow, just because it has to be character by character. And then lastly, the biggest pain point with building this peer-to-peer network was creating automated tests for it. Right now, or the majority of the testing was done manually. So we got into our application, started collaborating with each other, and we try and find bugs that way and try and make different scenarios. But it's a lot of manual testing, so it's inefficient and it's slow. So we want to create more automated tests for this. Some ideas we're kind of playing around with this is spinning up some EC2 instances, having scripts that kind of talk to each other. So that's kind of the idea we're playing around with. We just haven't gotten to it yet. And then also, if these optimizations, or if you guys play with Conclave and want to collaborate or contribute, feel free. We've released it so far. We've been getting issues and stuff like that, and we've been tackling them. So it's been a lot of fun. So yeah, if you feel like if you play around with it, find bugs. There's still plenty of bugs. So if you find bugs and you want to report an issue or try and tackle it yourself, go ahead. I definitely would love that. And so yeah, that's it so far. So thanks a lot for listening to me. And it was a lot of fun speaking. My name again is Beatteay. Here's my contact information, my email address, and my website. A quick note is that I am looking for new full-time opportunities right now. So if you know of any open positions, or if you know if your company is hiring a developer and you think my skill set would be valuable, let me know. You can talk to me directly with my email address, or just come talk to me after this. I'm definitely open. And then if you want to learn more about Conclave itself, I would definitely advise going to this project page that has our case study there. It also has links to our repo and the application itself. And if you enjoy using Conclave and the editor itself and you want to embed it into your own project, we have an embeddable version called Conclavity. You can go there. This links to the repo, and you can has instructions for embedding it into your project. And then lastly, I'm going to have a quick demo. So I'm going to allow all of you to collaborate together. This is definitely the biggest group that we've had test it live. So I'm not making any promises. Things probably will go awry, but if you want to try it out, I definitely want to test it as well. So let me just, so don't go to this link yet. This link doesn't exist, but I'm going to create it real fast. All right, so it should exist now. So if you go to that link, yep, people are starting to join. So yeah, you can start collaborating. Yeah, and then I'm willing to take questions now as well.
Any questions?
Yeah.
You mentioned you put a delete operations in the buffer because a delete could potentially be dependent on an insert that hasn't arrived yet, right?
Mm-hmm.
Could that be possible with an insert? For example, inserting a character after a character that doesn't exist yet, according to one peer?
Say it one more time. So the question was to put inserts into the buffer just in case we receive an insert that's too far ahead, essentially?
Like if peer 1 inserts a character, peer 2 inserts a character after that one, but peer 3 hasn't seen either insert yet.
So that in that case, because so the question, I think you all heard the question.
I'm picking up audio, okay, so you don't have to repeat the question.
Okay, so in that case, because of the position, the relative position, it doesn't really matter what order we receive the inserts in, because if the second insert was created after that initial first one, if they come out of order to peer 3, because those inserts we can if you write her and then RE or the R or she comes first, we'll put the R in and then the E, and then so technically we're writing it backwards, but because of the it's fast enough that it's not really noticeable, but it's not really a big issue. Like we're not too worried about the words, the inserts coming out of order. It's much more the deletes. Any other questions?
I used it and I noticed that you had like these animal text avatars.
Yeah.
So do you have to use those, or can you use other names? It wasn't clear to me.
Yeah, so those ones, right now you have to use those, just because it's actually kind of fun. What we did for that.
I don't know who you're talking to.
Yeah, you want to know who you're talking to. We could make it with more names as possible. I think just for the sake of speed, we just had it we have a huge array of names, and so whenever someone joins, you give it an ID. We hash that ID down to an index and just pick a name from random on that array. So that's how that works.
So I opened up multiple instances on the browser.
Yeah.
Do you plan on maybe doing some type of caching so you don't have that situation?
Say it one more time.
Because you know how you can open up multiple tabs on the browser, so open up multiple instances so each one is a separate entity of their own. So perhaps I was thinking of some cache cookies so you don't have to do that, so it doesn't work. Is that something you're thinking about in the future?
So what do you mean? So in that case, if we...
Oh yeah, because I have one tab with Sparrow, and then the next tab I'm also Robring, and then open them another tab and I'm somebody else.
Yeah.
So have the
I got you. So
same user.
Multiple tabs in the same user. We could do that. The reason why we actually didn't do that is just for testing purposes. In order to test it real quickly, we just open up a bunch of tabs and collaborate together, just by yourself. That is possible, but for testing purposes, until we create those automated tests, we use that sharing link, that tab, like the sharing link, to quickly open tabs and test it. So that's what we use it for now. Good. All right. Cool.
Awesome. Thank you.
Yeah, thanks, guys.
Up next we have,